You know that glowing screen in the middle of your car's dashboard? It looks, well, like a tablet, right? But behind that glass is a digital engine that's every bit as complex and as critical as the one under the hood. So today, we're going to pull back the curtain on the massive software operation that powers your in-car experience, taking you all the way from raw source code to the final polished display in your cabin. First up, we're going to bust the myth that your car's screen is just a tablet. Then, we'll take a deep dive into how developers actually build the car's operating system from the ground up. We'll see how all that code becomes a real product you can touch. Then, we'll explore the AI copilot that it enables. And finally, we'll take a look at what's just around the corner on the road ahead. Okay, let's just get right into it. The first and most important thing to wrap your head around is that the system running your car is not just some glorified phone app. It's way, way deeper than that. It's the vehicle's central nervous system. Now, a lot of us are familiar with Android Auto. You plug your phone in, and boom, a version of its screen shows up in your car. But that's just a projection. What we're talking about today is Android Automotive OS. This is something totally different. This is the car's own native brain. It runs directly on the vehicle's hardware, and it doesn't need your phone to do a single thing. So here's the bottom line. Android Automotive OS is a complete, full-fledged operating system that's built from the ground up specifically for cars. It's not just playing your music or showing you a map, it's deeply integrated into the car itself. It's capable of controlling core vehicle functions, and it's really the foundation for all the incredible smart features we're starting to see in modern vehicles. So now that we know what it is, let's get into the really fascinating part. How is this ridiculously complex piece of software actually made? This isn't like just downloading an app from the App Store. Oh no, this is a fundamental creation process that literally starts with mountains of raw source code. You know, the best way to think about this is like baking an incredibly complex, multi-layered cake, and you're not using a box mix here. You're like a master chef, sourcing rare ingredients from all over the world, prepping your kitchen with super specialized tools, and following a recipe that is so precise, one wrong move could ruin the entire thing. And this is basically what that recipe looks like. First, a developer sets up a seriously powerful Linux computer. That's their workbench. Then they gather up all the source code, the ingredients, from a bunch of different places. Next, using a command that's, get this, actually called lunch, they tell the system exactly what kind of cake they're baking. And finally, they run one single command that kicks off the build process, which is basically the automated oven that takes all those raw code ingredients and bakes them into the final OS. And this whole process is so intense, it can take hours and hours to finish. And to give you a sense of scale, this is not something you're doing on your laptop. No way. The documentation shows that developers need at least 450 gigabytes of free space on their hard drive, just to hold the source code and the files that get created during the build. That's the minimum for the workbench. So what about those ingredients? Well, it's not one single download. The final OS is an assembly of code from all over the place. You've got the public Android code from Google, you've got public and proprietary code from the chipmaker, like NXP, and then you have the foundational code like U-Boot. That's the very first program that runs to wake the whole system up, and the Linux kernel, which is the absolute core that manages all the car's hardware. It's a really complex software supply chain. Okay, so after all that work, sourcing the code, configuring the build, waiting hours for it to compile, what does a developer actually have at the end of the day? How does this wall of text and code turn into that smooth, slick interface you see in the cabin? Well, it turns out they don't just create one final version. They actually create several. There's the ENG, or engineering build, which is totally wide open with all the tools for developers to poke around in. Then there's user debug, which is a lot closer to the final product, but still lets them do some testing. And finally, you have the user build. That's the lockdown, optimized, and super secure version that actually ships in the car that you buy. And this is a perfect example of why those different builds are so critical. I mean, to develop and test a feature as insanely complex as a 360-degree camera system, engineers need that deep under-the-hood access that the Eng and user debug modes give them. They can simulate inputs, they can check sensor data, and they can perfect the whole experience before they lock it down for the final user version. So, at the very end of that whole process, the output isn't an app you can clip on. It's a set of core files: system.img, boot.img, vendor.img. You can think of these as the digital blueprints for the car's brain. They contain the entire operating system, all the drivers for the hardware, absolutely everything needed to bring the car's digital experience to life when they're flashed onto the vehicle's internal storage.
So we've got the blueprint, but a blueprint needs an engine to actually make it go. And this is where things start to get really futuristic. This advanced software is powering an experience that's becoming less of an interface you tap on and more of an intelligent co-pilot that works with you.
That digital blueprint we just saw being built, it needs to run on incredibly powerful, specialized hardware. A perfect example is NXP's i.MX 95 family of processors. These things are designed from the ground up specifically for these demanding automotive jobs. They're the physical brain that executes our digital blueprint. And all this leads to a really powerful concept called sensor fusion. Dan Loop from NXP put it perfectly. He said, AI-powered sensor fusion allows the car to give the driver more accurate and usable information about what's happening in and around it. Basically, it's about using AI to intelligently combine the data from multiple sensors, cameras, radar, you name it, to create a single, unified understanding of the world that's way more accurate than any single sensor could be on its own.
So what does that get you? What does that actually mean in the real world? Well, it enables some truly next-generation features. Things like driver monitoring systems that can tell if you're getting drowsy, child presence detection, which is a crucial safety feature that can sense if a child has been left behind in a vehicle. Even the displays get smarter, using things like local dimming to improve contrast and save energy. This is really where the software and the hardware come together to create real, tangible benefits for our safety and convenience. Okay, we've seen how this digital engine is built and what it can do today. But the pace of change here is just accelerating like crazy. So let's jump to our final section and see how this all builds toward the future of the car itself.
I mean, just look at the last decade or so. The evolution has been stunning. We went from these clunky, separate systems for maps and radio to just projecting our phones onto the screen. Now we're in the era of fully integrated operating systems. So what's the next logical step? Well, it's already starting. It's the true AI co-pilot, a system that doesn't just react to what you tell it to do, but actually proactively assists you based on its rich understanding of the car and everything around it.
Of course, there's a huge catch. When your car becomes a powerful, connected supercomputer, security becomes absolutely paramount. And this is critical, right? Because securing a car isn't like securing your phone. A hack here doesn't just mean your data gets stolen. It could have real-world physical consequences. That's why chip makers are building in technology with a name straight out of science fiction, post-quantum cryptography. Put simply, the encryption we use today could one day be broken by the unbelievably powerful quantum computers of the future. So this is like a new kind of digital lock, one that's built to be so tough that even those future supercomputers can't pick it.
Which brings us to a final, really crucial thought. We've seen how this digital engine is meticulously built from raw code, baked into a powerful OS, and fused with AI to become an intelligent co-pilot. But as our car becomes a supercomputer on wheels, it also inevitably becomes a target. So as we hand over more and more control to these systems, we have to ask ourselves, who is truly in the driver's seat when it comes to keeping it all secure?